Okay, this will be this is the last recording, the last problem we'll do, and I'm going to add just a little bit more as I'm going to go back to the slides, and we're going to talk about the electric field for a minute, just because I wanted to get that covered today too in class. So anyway, here's where we're applying a force that we learned about last week. And one of the things that I like, this is one of those go problems, and I've assigned two of them back to back. And I was surprised that when I asked in class today, out of the 20 or so that were left, out of the 130 of you, which is fine. I mean, hey, I get that. Um, uh, Several did not know about the Go tutorial, and that's why I assign these problems so that you can walk your way through them. So you might be going, well, then why are you doing this one? Why don't you do another one? Because I want to do this one. Because I know how to do this one. So anyway, all right, but this is where we're asking from, now, an unrestrained horizontal spring. Is 0.3 meters long, okay, and that's constant, but two small charged objects are attached to this spring, okay, one at each end. The charges on the objects have equal magnitudes. Because of these charges, the spring stretches. The spring stretches. So we'll draw a picture of that too. And it says determine the possible algebraic signs of the chart and the magnitude of the charge. The magnitude, notice again the magnitude and not the direction, because, well, charges, of course, the magnitude of a charge is a scalar. The force, the Coulomb's law, is a vector. So here we go. Let's draw the picture and take a look at what this looks like. So here's the picture. Got these two charges. We place these two charges on the end of this spring. I'm going to make it a spring now. All right, and they are 0.3 meters apart. Okay. Now all of a sudden, something happens, right? Something happens. So we put charge on these things. So now they're charged. Let's go show their charge, because I don't know what kind of charge was put on them. And they stretched out a little bit. So we don't know what kind of charge. And now they're stretched out to 0.33 meters apart, where length 2 minus length 1 is equal to 0.03 meters. Is that correct? Yeah, okay. 0.03 meters apart. So this is my delta L, or delta K, or delta X. Sorry. I should have said X2 minus X1. X2 minus X1. Or triple X with Vin Diesel. Give me a break. Anyway, do you remember? This is a spring where it had K, force constant, of 200 newtons per meter. Again, a confusing thing. They might have put this on here just for this. This is referring to the spring constant. This K is referring to the electric constant. Wow, physics is easy. Context, 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 I guess. All right, but look, do you remember Hooke's law? F equals kx. This k and this k times x. I put delta t there. K times x, you remember that? Yes, you do. And that's the same force is equal to k times delta x. That is equal to these charges. And obviously they're repelling each other. The force on 2 caused by 1 is going this way, and the force on 1 caused by 2 is going this way. So obviously they're repelling each other. They're going against each. Get my hands in. Going against each other. You know, they're. So what do we know about those charges? Do we know Are they positive? We don't really know for sure. Are they negative? Don't really know for sure. Is one positive and one negative? No, that's impossible. Otherwise, they'd be pointing towards each other. So this is the spring constant. Spring equals K electric constant times. Now, I think we put the same amount of charge on there again, so we've got Q squared because Q1 is equal to Q2, which we'll just say is equal to Q squared over the delta X squared. Okay? Makes for an interesting problem to find Q. Wow. I'm going to do it. I'm hoping that's what they're asking. The magnitude, yeah, the magnitude of the charge. There we go. The algebra on this comes out to be kind of unique. Because look, you get K of the spring times delta X cubed is equal to the electric thing times Q squared. These K's do not cancel because they're two different things. So Q is equal to K of the spring delta X cubed over KE square root. All right, that is quite a thing. Look at that. I wonder if that comes out to be coulombs if we did the unit analysis. When we're in electricity and magnetism, you start doing unit analysis, ooh, it is ugly. It is so ugly. But bear with me for 3 minutes. I'm going to do that real quick. You can skip this part. This part is not for children. All right. So the spring constant is in newtons per meter, which is a newton, remember, is a kilogram. So I got a kilogram meter times meters per second squared. Okay, that's in the numerator. Times meters cubed. That's there. Okay, divided by KE. Divided by KE, which is equal to, okay, because this is my delta X cubed and all that stuff. All right, divided by KE, which is equal to a Newton. Aha! Going to get a Newton, which is a Newton times meter squared divided by Coulomb squared. All right, so look what we've got here. In fact, I can just do Newton per meter, because that's my K. This is my K. And this is that. So look what happens here. This meter goes away. Well, basically what I got is I've got a Newton per meter times meters cubed. Okay, that's in the numerator. All right, and in the denominator, I have a Newton per meter squared divided by C squared, Coulomb squared. Told you, give me 3 minutes or so. Newtons cancel. That cancels, and that gives me an M squared over M squared over C squared, which is the same thing as M squared over 1 times C squared over M squared. Bang, bang, that equals C squared. It's all under the square root. It does come out to be coulombs. Pretty amazing. Don't you love when a plan comes together? That probably made your head hurt. Sorry. All right, we got one more track.